All right, let's get to work on WebAssign. All right, so for this last assignment, here's problem one. I got this figure with a crate of some mass, blah, 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 pushed at constant speed at the frictionless ramp with a certain angle by horizontal force. Frictionless ramps, gotta love them. Don't happen very often in nature. So, anyway, one, two, 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 two. So there is our ramp, got an angle, two, 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 and this is one of my uglier ramps. Hope everyone had a happy Thanksgiving, by the way. All right, so there's our mass, crate of mass m, and there's our horizontal force F, and it is pushed at, I believe the assignment said, a constant speed. So v equals constant. And what that means is if our velocity is constant, our acceleration is 0. Ooh, okay, fancy. So let's do a free body diagram. I'm going to use sort of a dark maroon red. FBD for the crate. And what are the forces acting on the crate? Well, let's just draw them out. There's the weight, mg. There's our normal force, and we already have F in there. Boom, boom, ba-doom. Let's pick some coordinate axes. Let's just go with X going up the ramp and Y like that. So let's see. Since our acceleration is 0, in both cases, we don't really care what coordinate frame we use. So actually, I probably could have. What the hell? All right, so let's do it. Now, you know what? I'm gonna do. I love being wishy-washy. All right, I'm gonna do. Since our acceleration is 0, we can basically pick any coordinate frame because whatever coordinate frame we rotate this thing into will still be acceleration 0. So let's draw our coordinate frame like that. Standard, left, right, up, down stuff. All right, so FBD for the crate. We've got. There's our crate. There is our normal force. That is at an angle theta off of vertical. We've got our applied force F coming in, but actually that's wrong. We're supposed to draw that as a pull. Bad teacher. Bad teacher. All right. And there's our weight of the crate. Fantastic. Oop, forgot to draw our coordinate system in, so let's do that. X and Y. And then let's flesh it out. So there's n cosine theta. This way we have n sine theta. Here we have our applied force F, and there we have mg. Okay, so sum of forces in the x direction equals 0 because it's not moving. So force in the x direction, F minus n, capital N, n sine theta equals 0, which means F equals n sine theta. Sum of forces in the y direction equals 0. So that means n cosine theta minus mg equals 0. And then n cosine theta equals mg. And then we get n equals mg over cosine theta. Well, couldn't really be much easier than that. We take this n here, we plug it into there. So this sort of lavendery color. We take that, plug it in here, and we get to F equals mg, and then it's over cosine theta times sine theta. So sine over cosine is going to be equal to tangent of theta. And so I believe that will give us the correct answer, right? So the previewer, yep. And all right, so mg tan theta. So let me pull out my fancy dancy little calculator here. So let's see, mg tan theta was our m, 250. 250 times g times tangent of 33 is, oh, right, of course, this calculator doesn't know g. So I'll just use 9.81, why not? And there's 1592.6, so I'll call it 1593 newtons. 1593 newtons. Perfect. And then what's the magnitude of the force exerted by the ramp on the crate? That's right there. Well, that's just the normal force, right? There's no friction force. The only force the ramp exerts on the crate is the normal force, and that is that's going to be, well, we can just say it's fine, mg over cosine theta. Let's just do it that way. All right. So 250 times 9.8 divided by cosine of 33 is 2921. So let's see, 2921 newtons, and Boom, boom, done.